Yeah, so welcome everyone. So this is the part of the NSF-Simons Cosmic AI so Institute seminar. This is a new kind of institute, and it's kind of building an institute for kind of astronomy challenges, especially about cosmic origin and artificial intelligence. It's part of the one of the sites is Utah. This is the first instance of the seminar we're hosting here in Utah. There are other people online, and so with the first seminar, I'm very pleased to have Varun Shankar speaking. Varun was a PhD student here as well here in the Ski Institute, where we're allowed to use their room. We're working in problems in scientific computing. He did then a postdoc in the math department. Then we managed to hire him back to the School of Computing, where he helped build up this master's in software development program, while somehow managing to run a research program at the same time. After a couple of years later, we figured out we should hire him on the tenure track faculty. Since then, he's been doing this amazing work using scientific machine learning. And today he's going to be talking about kind of his recent work and using that for surrogate modeling, hopefully with some applications towards astronomy. Great, so thank you.
Thank you, Jeff, for the very kind introduction. I also wanted to, I've said this to a few people and you're going to hear it again. This is astronomy is a lifelong passion of mine, but just a hobby, right? So it's nice if you can merge your hobbies with work, or at least I think so. Thank you. This is a privilege. I'm going to enjoy giving this talk. I have way too many slides, so we're going to probably omit some stuff in the middle, but I have a plan for that too. The title is Structure Preserving Low Parameter Interpretable Operator Learning for Surrogate Modeling. That's a mouthful. The secret title is Kernels Are Awesome for Operator Learning. Okay, and we're going to talk about this in some detail. The high-level outline of the talk is, first I want to tell people what operator learning is, in case you haven't seen it, or maybe you've seen it, you've been curious, you wanted more details. And so I'm going to present like a common framework that covers various different kinds of operator learning techniques, and then show that each of them is an instance of that framework. It turns out that's actually pretty easy to do. And then I'm going to discuss some work with my student Matt, who's sitting right there, chewing on something. This is the Kernel Neural Operator that we developed with Matt, John Tanaj, who's here, and some folks at Sandia, and Akhil Narayan. I don't see here. It's cool. Then if we have time, this is the part I might throw out, but if we have time, we'll talk about the work with Ram, who's sitting in the second row there, or the third, fourth row there, second row from the back. And this is ensemble DeepONets. And then finally, discuss some ongoing work with Ram and Huma Nawadi at Caltech, which is using kernel methods and Gaussian processes for operator learning. I have one slide at the end in terms of implications for astrophysics, but it's a good slide. Okay, so just an overview. Scientific machine learning, I think of it as scientific computing principles meeting machine learning, and with a sprinkle of high-performance computing thrown in, if that's your jam. But the goal that we have in my lab, and that a lot of scientific machine learning folks have these days, is to develop surrogate models that can replace either entire numerical solvers for PDEs or expensive parts of numerical solvers for PDEs, right? The parts that you simply cannot tolerate computing. The goal, of course, is rapid inference, whether you're doing it at the solver level or at the subscale level as part of the overall solver. And of course, the goal is correctness. And the question is, can we say things about correctness a priori instead of we tried the model and it works? Right? This is sort of the goal of scientific machine learning as a community or as a field. How do we do this? There's actually many ways to do this. There's entire industries of techniques out there, but I'm going to be focusing on operator learning today because that's what we do in our lab. Okay, so the idea of operator learning is actually really simple. You learn a map between function spaces using data. I'll give you a concrete example of operators. We've all seen them. derivatives are operators, integrals are operators, the plus symbol is an operator, right? But more interesting examples of operators, if you're working with PDE, in the PDE world, in partial differential equation land, is Green's functions, which are solution operators to PDEs. Or in general, when you don't know the Green's function, the question is, can you learn a reasonable substitute for the PDE solution operator? Right? This is sort of the goal here. Okay, let's ground this in a concrete example. So I've just written down the heat equation, the forced diffusion equation with some boundary condition. We don't care which one. This is just for a talk, right? And some initial condition. And I want to just sort of go over what operator learning problems you could think of as being associated with this system, right? So for instance, if I have a solver for the heat equation and I want to replace it with a surrogate, what are different ways, different kinds of surrogates I might need in practical contexts? So for instance, I might want to learn the map from the space of all possible initial conditions to all possible solutions at some final time t, given some f and given some boundary condition and given some domain, right? This is one example of an operator learning problem. And then the idea is, if someone gives you a new initial condition that was not in your training set, you just shove it through the operator you learned and get out the solution without having to solve the PDE all over. Right? This is the high-level idea behind operator learning. But there's other operator learning problems that I could associate with this simple PDE. So for instance, I could say, I want to learn a map from not the initial condition to the solution at some final time, but the initial condition to the solution over some time interval. Right? So a map from a spatial function to some space-time function. And that's also a useful operator learning problem to solve, because then you get temporal slices of your solution wherever you want over that interval. If you're lucky and your method was good, you might even be able to extrapolate, but I wouldn't recommend it, right? Okay, so you could also, for instance, another reasonable thing is to say, I'll pin the initial condition, but I want to learn the map from some nonlinear forcing term to the solution at some final time t. I have identified like single pieces and I'm mapping them to solutions, but you could imagine combinations, initial condition and boundary conditions to the solution and so forth. And all these are possible, okay? So I'm saying spaces of all possible initial conditions, spaces of all possible solutions. What kinds of spaces am I talking about? These are function spaces, right? And so we're explicitly thinking of learning a map from one function space U to another function space V. G is the operator that takes functions from U and produces functions in V, right? So derivatives, for instance, produce things often in the same space or perhaps in a weaker space, depending on what you're talking about. But this is not a learning problem. You can't do anything with this. All you can do is write a notation, a piece of notation on a slide. If you actually want to solve this infinite dimensional problem, you have to actually solve a finite dimensional version of this instead. And so the idea is, well, how do we proceed doing that? So obviously the first step is I'm learning a map from U to V. I better have examples of functions from U and V. I like to call them examples. You can think of them as samples also. But basically, I need to see as much of U and as much of V as I can, or as is important. But even if I draw a bunch of functions from function spaces, that doesn't turn the problem into a finite dimensional one, just an infinite dimensional one of a different flavor. So I actually need to sample these functions on their domains. Like literally put down space-time grids or something and evaluate. And get a vector space embedding of it in Rm. Then you learn the vector map from Rn to Rm, right? And that's the goal. That is a finite dimensional learning problem. If you can learn a map from a vector space to another, which by the way, we do all the time in machine learning, in traditional approximation, this is sort of a problem that's been tackled for a long time, right? And we're just bringing some interesting new perspectives to this. Then you can always recover the continuous operator or some approximation to the continuous operator by just walking this diagram. So for instance, if you want to learn the operator G, compose chi with F with phi, and that's actually G. You can walk the diagram in various ways to get things that you want. I like this diagram because it actually covers all existing neural operators out there. Okay, we'll talk about that in detail. So what do you actually do? You're given pairs of functions ui, vi. They're sampled on their appropriate domains, and you minimize some objective function. In this case, I've written down an L2 objective function. And now you have to make choices for all these little symbols, squiggly symbols that are on the arrows, right? So I have to parameterize F in some way, I have to parameterize phi in some way, and parameterize chi in some way. And the different choices of parameterizations lead to varieties of operator learning techniques. The first one is the first one that maybe chronologically also the first one, at least in terms of machine learning, is DeepONets or deep operator networks, right? So DeepONets came out in 2019, and the idea is really simple. You basically take point samples of your input functions, U, and learn a linear combination of basis functions that fit the output functions, V. That's it, right? So take in the input functions, embed them into some vector space. That's a fancy way of saying sample the function, and then learn some linear combination of basis functions. The basis functions in DeepONets are deep feed-forward neural nets, or in general, they can be neural networks of any sort. That's what makes it a deep operator network. And so that's called the trunk in DeepONet terminology. It's the trunk net. Then you have a linear combination of basis functions. So you need a bunch of coefficients to combine the trunk. Those coefficients are called the branch. So there's a neural net that produces the branch coefficients. It's called the branch net, right? So the DeepONet is merely a dot product between two neural nets. That's the way I think of this. Okay. So that's DeepONets, and these are highly effective. If we have time, there's a chunk of my talk where we talk about extending DeepONet's capabilities to handle sort of local solution features. Another really popular neural operator is the Fourier neural operator. It's actually highly effective. It turns out that without a lot of engineering, you can just apply it to a wide variety of problems, and it just works. And because it has some nice approximation properties. And the Fourier neural operator is not explicitly trying to do what the DeepONet is doing. So the DeepONet consumes samples of your input functions and learns a linear combination of basis functions. The Fourier neural operator is literally trying to construct a map from point samples of your input functions to point samples of the output function. Okay, that's the job of the Fourier neural operator. The way it looks, there's some complicated architecture that involves a lifting of your inputs and a projection. But the main idea behind the Fourier neural operator is the main workhorse behind the Fourier neural operator is a linear integral operator of the form integral over some domain against some kernel of some function. And so you basically take the output of one layer, shove it into this integral operator, evaluate it somehow in some fancy way, apply an activation, and then rinse and repeat. That's the Fourier neural operator. The interesting feature about the Fourier neural operator, and this will segue into my work, is you never actually specify what the kernel K is in the Fourier neural operator. You actually just compute it. So the idea is simple. You say, okay, I have some integral against a kernel K. I'll treat it as a circular convolution. If I treat this as a circular convolution, I can actually handle this in Fourier space. So I'll just apply the Fourier transform. What that does is, especially if F is a vector valued function, if you apply a Fourier transform to this, you get a multiplication in Fourier space, a matrix vector multiply in Fourier space, right? And even if you start out with a matrix valued kernel over here, which we never write out, in Fourier space, you get something that's block diagonal because it's periodic. You're implicitly assuming the kernels are periodic, so you get sort of block circulant matrices, in fact. Okay, so in the FNO, the Fourier neural operator, you directly learn the block diagonal entries of this kernel matrix K in Fourier space. Do the multiply, Fourier transform back, maybe chop off some frequencies before you Fourier transform back. transform that, right? So this actually works beautifully, but you have made certain assumptions on the nature of this kernel, right? One assumption that you have implicitly done is you've said that this kernel is periodic, which may be appropriate for some problems and may not be appropriate for other problems. There are other pieces in the Fourier neural operator that try to compensate for this periodic kernel and the problems that periodic kernels might cause. But we think there's maybe a different way of handling this, and that sort of will lead to our work. I do want to mention, that's neural operators, right? This is all machine learning. You're learning the entries of some kernel matrix, whether it's in Fourier space or not, or you're learning the weights of some neural net. You could also just do all of this using interpolation, right? So basically, you can formulate the problem of mapping from Rn to Rm as just interpolating a vector valued function at points in Rn. That's it, right? And so that perspective has also been leveraged by Huma Nawadi, collaborator of mine, where he used kernel-based maps to actually approximate that. And the last third of my talk is all about that, so we'll talk about it. Okay? I just want to point out, maybe you don't always have to use something neural. Maybe there's some other judicious choices that make sense in different contexts. I should also mention that John Ternage here is also working on some sort of kernel method for exactly in this setting. Okay, so I want to point out there's some sort of interpretability accuracy slider, right? On the one end, I have something that's based on interpolation, and I can look at the kernels that I get, and I can look at the coefficients, and I can really understand what's going on. I have error estimates in terms of the kernel smoothness and the target function smoothness, so I can prove things in advance for the most part. In the neural setting, I have something that's expressive, but has like potentially millions of parameters. And so there's some sort of slider here that lets me sort of toggle between accuracy and really understanding what I'm doing, which is a worrying sort of slider to have. And so basically I want to ask 3 questions, and the remaining 3 chunks of my talk will answer each of these 3 questions, or will provide some evidence for these 3 questions. So the first is, can we do something in operator learning that uses low parameter counts and gives you some interpretability without sacrificing accuracy? Do you really need all those parameters, or can you make do with fewer? The second thing is, can we do things in neural operators, in operator learning, that we do with traditional numerical methods, scientific computing, which is build features into our sort of operator learning technique, which is maybe I have a locality prior. Maybe I know that in some part of the domain, my solution is localized. Maybe I know that the operator needs to be sparse in some sense, right? Is there a way to bake these things into the operator? That's the second piece. And the third piece is, and this is the one that's really exciting to me, but you'll have to wait till the end of the talk, which is, can we build neural operators that respect physics analytically? Meaning, I specify X physical property, and we satisfy that property to machine precision. Right? So we're going to tackle all 3 pieces. The second piece, I might have to like skim over it depending on how fast the rest of the talk goes. Okay, so to tackle the first question, I want to present the kernel neural operator. It's not going to look very different from the FNO, but it has certain key differences that makes it more flexible and powerful in some ways. So in other words, I'm going to present a new neural operator. This is work with Matt and John and Sandia folks, which has lower parameter counts, far orders of magnitude lower parameter counts in some cases than the FNO, but is able to provide similar accuracy and similar expressibility. But because we sort of know what the kernels are, we're able to interpret our operator better. Okay, so setup. At the high level, it looks really a lot like the FNO. We're again mapping point samples to point samples. We have some lift and some projection of the input and of the output. And we again have an integral operator of this form, a linear integral operator of this form. You might say, what's different? So in the FNO, the Fourier neural operator, this integral operator was handled via convolution, meaning it's handled by a Fourier transform, right? I pointed out that imposes some sort of periodic structure on the kernel. In other words, you can think of it 2 ways. You're either only allowed to plug in periodic kernels into this expression, or you're only allowed to learn periodic kernels. Think of it however you want. These are equivalent perspectives, right? So the difference in the Fourier neural operator is that we actually specify a formula for the kernel. We don't learn the kernel entries directly, the kernel matrix entries directly in Fourier space. We stay in real space, or whichever domain we're in, and just write out a formula for the kernel. So maybe we say it's a Gaussian kernel or something else. And I'll talk about kernel choices in a couple of slides. Okay, so then by specifying the kernel and not having to learn all the kernel matrix entries directly, most kernels have 1 or 2 parameters that you have to learn. So instead of learning a ton of parameters in a matrix, you just learn 1 parameter, and that helps you fill out that matrix appropriately, right? But by not going to Fourier space, you have to tackle that integral in some way. And so we just use quadrature, numerical integration, right? And this combination leads to the kernel neural operator. What kind of quadrature? Well, I just want to point out, you can still do the FFT if you picked a periodic kernel. So in the base case, this reduces back to the FNO because you can integrate periodic kernels with the FFT. But in the more general case, our framework allows for arbitrary quadrature rules. We've experimented with all sorts of things, sort of traditional tensor product, Gauss-Legendre quadrature, or we've also done things like quadrature on triangle meshes. Matt ran an example for a paper that was like a meshless quadrature rule that was in a ball. As long as we can generate a quadrature rule, we can basically plug it into the KNO, and there's also ways to generate these quadrature rules. Yes.
So where's the quadrature happening? Is this in the space of the infinite dimensional?
No. So yeah, that's a good question. So the quadrature is in the space of whatever function is coming into it's in the domain of whichever function is being consumed by the integral operator. And so that's usually the domain of the input and output functions. So it's not in the infinite dimensional space. It's in some finite.
In the domain of uppercase U and uppercase V.
It is in the domain of lowercase u and lowercase u. Yeah, that's right. Yeah. So think like a spatial domain or a spatiotemporal domain, right? It's in the domain of the solutions to your PDEs. Does that make sense?
And how are those spaces parameters? What's an example of a function that space you work with? You showed these 2-dimensional domains.
Oh yeah. So since the focus of my talk is on sort of PDEs, all the domains in this talk are PDE domains. So for instance, I want to figure out how much heat is diffusing in a box. The domain is a box of the unit cube, unit hypercube or something. In this case, this was a quadrature rule in a ball because we wanted to do reaction diffusion in a ball. And so we needed some way to integrate over that volume. And then if you have a time dimension, then you want a space-time quadrature rule similarly. So you can generate these in some smart way, or you can just tensor product 1D things and get out whatever you want. Not that that's not smart. Okay. So yeah, does that make sense? Okay. So we've experimented with all this, right? But there's one little caveat here. Your training data does not live at the quadrature points, right? But all your integrals need to be evaluated at quadrature points. So you need to move data somehow from your training points to your quadrature points, right? Data needs to live where you need to compute your integrals. The simple solution is to interpolate or regress to do that. And so we just use, we sort of wanted the most flexible framework. We thought about neural nets initially, but then we realized there's something even simpler that we can use. We just use kernel-based interpolants. I'll discuss those in a lot of detail later. But the idea is that even if your data is scattered and not living on any mesh, these kernel-based interpolants still converge. They're non-singular. They have nice properties. And I've worked with them for 15 years, so I know what I'm doing there. Yeah, this is the idea. And so just fit the training data at the training points, wherever those are, and then just evaluate the interpolant at the quadrature points. You have transferred information. Okay? And that's it. And then proceed, integrate. You can always, these things are functions. Even if I plug in quadrature, all I've done is discretize the variable y. I can evaluate this at any x that I want to get an output anywhere in space. So I think of the FNO and the KNO, if it helps, the mental analogy I have is I think of the FNO and KNO as function space analogs of standard neural nets, of MLPs, where each layer is now continuous in width rather than having a finite number of neurons. I think that's the closest analogy here. Depth is still discrete, but we're working on that. Okay, so what kernels should I use? I've been hand-waving that. Use whichever kernels you think are appropriate for the problem, right? Make reasonable choices instead of just learning the kernel matrix's entries directly. So for instance, if you think that your kernels need to be sparse because the solution operator is sparse or localized in some way, we can stick a kernel in there with trainable sparsity. That's the one I'm showing you here. This is a compactly supported positive definite kernel with a free parameter epsilon. That epsilon actually determines the support or the region of support of this kernel, but also it determines how sparse it is because it's the region of support. We've also experimented with other things. So for instance, if you're learning a map, so remember we're learning a map between two function spaces. If you're learning a map from like a function space that has very smooth functions in it, but on the other side, you're learning the map has something that produces rough functions. Maybe you want kernels that are rough, that start off smooth in the earlier layers of your neural operator and then become rougher as you go through the composition, right? And our framework actually allows us to do this. If you really want to throw a hammer at it, there's a spectral mixture kernel that Matt likes to use, the Gaussian spectral mixture kernel, which has, what, 2 times 2D plus 1 parameters, which is still nowhere as many parameters as learning the entries of some matrix directly, right? So just some results. We've tested this on learning solutions to different kinds of PDEs. These are PDEs that one might care about. Burgers and advection were in 1D. We did Navier-Stokes in 2D, and all 4 Darcy problems were in 2D. And then there's a more tricky 3D reaction diffusion problem in the ball. The point is not to say, oh, look, like we got better accuracy and everything. Sometimes we may or sometimes we may not, but we're in the same ballpark as other neural operators. It looks like at least on all these test cases, we did much better, except the bottom row and maybe the second row. There's good reasons for that though. So in the second row, just interpolation gives you 13 digits of accuracy because it's a linear, the solution operator is linear and the kernel they used was linear. But this is a good thing, right? This tells us like, if you can tailor your kernel properly to the problem, you can just destroy other methods, right? So, but more importantly, I think, look at our parameter counts, right? So the kernel neural operator, which is in the last column, often has like a couple of orders or sometimes 3 orders of magnitude fewer parameters, trainable parameters. So our models are much smaller, right? Literally on disk or in memory, they're way smaller. They're still expressive because you're still learning a kernel. If you wanted more parameters, there's ways to do that too. Just add more parameters to your kernels. But it shows that at least for the benchmark cases that people care that are out there, you don't need as many parameters as people think you need. Right? This is sort of my high-level takeaway. Outro, the KNO allows us to tailor quadrature rules to problems of interest, tailor kernels to problems of interest, learn surrogates on scattered data because we use kernels everywhere. And then we can, when we look at the kernels that we end up learning, we can actually see what they are because we have them as continuous functions, not just the entries of some matrix. Right? So there's some notion of interpretability here. For instance, we noticed on problems where we were learning more localized things, our kernels ended up being more sparse. On problems where we ended up learning more global-looking solution operators to PDEs, our kernels ended up more dense. Right? This is sanity. Okay, it looks like based on how I'm going, I might have to speed through this section, but that's okay. So this is the question I want to ask, which is, can we actually impose other properties into our neural operators, such as locality and sparsity? Just a quick thought experiment for this. If you were just doing interpolation or regression, and I said, I want you to impose sparsity and locality, where would you do it? In traditional settings. you really have only two places you can do it. You can do it in the basis functions, or you can do it in the coefficients. These are your two options. If you do it in your coefficients, that falls under the umbrella of compressed sensing. And you impose some sort of L1 optimization or some L1 regularization, and you get sparse coefficient vectors. If you do it in your basis functions, you typically express that your basis functions have compact support of some sort, and then you end up with sparse bases. If you're doing finite element or Galerkin types of things, you can also throw it into test functions, but just in case someone got upset about that. So we can now, in this diagram, we have to ask where we want sparsity and where we want locality, right? So the goal is to approximate these output functions V from the space capital V. And so if you think that there should be sparsity in the basis there, that's where we want to throw it in. If you think there should be sparsity in the basis on the U side, throw it in there, right? Everything I'm going to show you here is enforcing sparsity and locality in the basis for V, but there's a catch. In general, for a PDE that you've never seen, you actually don't know whether you should enforce sparsity or not, or locality or not. In general, you don't know that in advance. If you don't know something, if you don't know that in advance, what should you do? Well, we just said we'll stick both global and localized basis functions into the trunk network of a DeepONet. And so this is a DeepONet. The trunk network, remember, is just the basis functions. So we have basis functions that are global, so neural nets that see the whole PDE solution domain. And then we have specially engineered things that see local features. How do you specially engineer this? Well, we did a really simple thing. We put down some patches on the domain, right? Spatially overlapping patches. Put down a different neural net on each patch, and then blend them together based on overlap of the patches. So we put down compactly supported blending functions on each patch. Make sure the blending functions sum to 1, otherwise you get weirdness. But if the blending functions sum to 1, you can prove this sort of thing has universal approximation capability. And this is called we call it the partition of unity mixture of experts method. Fancy, right? Mouthful. It's a mixture of experts because each neural net is an expert in its own region of space, and then you're mixing them, literally. So for instance, that's how you might generate these blending functions, right? So grab a compactly supported function like this Wendland kernel that I showed you about 4 or 5 slides ago, and then just divide by the sum of all the kernels, and that's going to make the sum 1 at each point in space. And then that basically gives you a way to localize. And then now if you know that some parts of your solution are more important, just put down more patches there, right? If you want to, you can refine more, put down more patches in some regions of space, keep it sparse in other regions of space, and you can sort of zoom in on local solution features that way. All we did was take a standard neural net and then take this partition of unity, POU, MOE trunk, and then stick them all into the trunk network of a DeepONet and then learn them all together. But there's one caveat, like an ML person looking at this may rightly say, look, the great success of ML was don't do anything like this. Just shut up and over-parameterize. Throw a bajillion parameters, that the problem goes away, right? So why not just make your global basis like really wide and really deep and not try and do all this partition of unity stuff? Why bother? So we decided to test that too, in the interest of fairness. So we did different kinds of combinations of basis functions, ensembles of basis functions. The exact labels are not important. Whenever you see vanilla, that's just having a standard neural net. Whenever you see POU, it's a spatial decomposition. When you see POD, that's a proper orthogonal decomposition of your training data. Very popular, very common. And this P+1 vanilla is the hammer, right? It's when we basically say, I'm going to make just one gigantic neural net that in theory has the same number of parameters as if you have all these individual nets together. And I'm not going to do anything localized or partition of unity. And so we're calling that the P+1 vanilla. Okay. It turns out, so just to test this hypothesis, like locality matters, sparsity matters, I cooked up a PDE. It's a PDE that shows up often in practical applications, but I basically cooked up a PDE where it's a reaction diffusion equation, and the reaction term has a jump in the middle of the domain. And you can see that in the output function right there. There's a nice sharp gradient. It's a reaction diffusion equation, so diffusion keeps smearing out the jump. But still, at every point, there's a steep gradient in the solution. And we just tried all these 6 different methods on this problem. And it turns out that whenever you have some combination of global modes through POD and local modes through this partition of unity, that's when you get the lowest errors. The partition of unity basis functions, they learn something really localized. They're able to pick up those sharp gradients. The POD mode sees everything, and so it's able to pick up global correlations. We did the same thing in 3D, and we saw the same thing again. In the 3D case, I think the wildly overparameterized network simply did not converge. Yeah, he's saying he agrees. Yeah. So yeah, the wildly overparameterized network did not converge, possibly because we didn't have the right toolbox of training techniques for it. But that's the point. We didn't have to do anything special for this, right? We just spatially patched out, and it just works better. So the lesson from this is basically this partition of unity mixture of experts idea allows you to build in sort of spatial locality into your operator learning techniques. Brute force overparameterization probably will work in every case, but you have to start thinking about training and GPU resource. And the nice thing is we did all this in the context of DeepONets, because in DeepONets, you can clearly identify a set of basis functions, clearly identify a set of coefficients, and so it falls back into a sort of traditional approximation paradigms. We understand how to work with this. You can do the same thing in FNOs also, and we have a little bit of speculation in our paper on how to do it for the FNO. Go look at it, but don't scoop us. Okay, wow, I'm surprised I'm on time. All right. So this is the last chunk of the talk, and it's sort of ongoing work, so don't scoop us again. But now I'm going to talk about not doing neural anything. I'll throw in some neural in the results just to show you it doesn't help much. But the idea is to use kernel methods or Gaussian processes to do operator learning. And I'm going to zoom in on the problem of incompressible flow simulation, right? Incompressible Navier-Stokes. That's going to be the rest of the talk. But for astrophysics folks, I want you to think MHD. That's on the horizon, right? No magnetic monopoles. We don't want those. All right. So now I'm going to explicitly answer the question of, can we build neural operators that analytically respect physics? Okay. And do they even have to be neural? I already spoiled this for you. They don't. They don't have to be neural. The idea is sort of, we tried different iterations, right? And we sort of converged on this idea, which is take any one of your input functions and expand them in terms of some basis functions. Take all your output functions and expand them in terms of some basis functions. This, by the way, is not by itself new. There are people doing it right there. Right now, they call it basis to basis mapping. But they've used neural nets for everything, right? I'm going to show you something much simpler that works surprisingly well and gives you sometimes orders of magnitude greater accuracy. So the idea is, if I have an expansion of every one of my input functions in terms of my basis functions, and I have an expansion of every one of my output functions in terms of my basis functions, the whole operator learning problem turns into one of mapping the input coefficients to the output coefficients. Rather than mapping point values to point values, I'll map weights to weights. It's actually a linear problem, right? So the question here is not that this is, the cool thing here is not, oh, like we'll map weights to weights. It's sort of an obvious thing depending on your background. But the question is, what basis should we use? And that's sort of the contribution of this next chunk. The big contribution here is, if you're interpolating vector fields that should be divergence-free, use a divergence-free basis. When I say a divergence-free basis, it is a basis that is analytically divergence-free. Meaning, if you differentiate the basis functions, divergence is 0. Right? And it turns out that kernels are super useful for this. Let me finally define what these kernels are. So think of a kernel as a function that takes 2 inputs and produces an output, if you want. In this case, I'm thinking of starting with a scalar valued kernel. So it's a kernel that takes 2 inputs in whatever RD you're in. And again, the D here is the domain. The the RD here is the domain of your PDE solution functions. We're in discrete space now, right? It's not in some high dimensional function space. But given any scalar valued positive definite kernel, meaning its corresponding matrix is also symmetric positive definite, you can generate a divergence-free kernel by calculus, just literally calculus. So take the curl with respect to the first argument and take the curl with respect to the second argument. This results in a matrix valued kernel, a little d by d matrix at each point in space, and the columns of that kernel are divergence-free. The nice thing if you do that is now if you take any interpolant using this kernel, linear combinations of divergence-free things are also divergence-free things. So this interpolant is analytically divergence-free. There's a simplification you can do for this formula up here if the kernel is radial, and we apply that. So what I'm going to do, because I care about incompressible flows, I'm going to actually learn a mapping from divergence-free kernel expansions to divergence-free kernel expansions. That's it. That's the idea here. And so now we have to learn maps between C's and D's. In DeepONets, the map if you wanted to learn this vector map from one space to another, used a neural net, we realized we can just use a kernel, right? In some sense, kernels are a limit of neural nets. They appear in the infinite width limits of neural nets, sort of. And there's ways to make kernels quite expressive also. So there's a little bit of head rotation you have to do in your head to actually comprehend how we do this, but I'll walk you through it. So remember, for every input function and every output function, you're learning these C's and D's. And that's just solving linear systems to learn the C's and D's. Once you've learned the C's and D's, so say you now have n coefficients here and m coefficients here, right? I'm now going to take each coefficient vector, there's n coefficients, and think of it as a point in an n-dimensional space. I can do this, right? Why not? I have no idea what that space looks like, but I can think of these as points in that space. And so now I can specify an interpolation problem where I'm saying that D's are a function of the C's, and I want to just learn that map. Right? Interpolation is saying, hey, I have something that's a function of space, fit it with basis functions that are a function of space. Now I'm saying I have a function of C, so I'll condition my basis functions on the C's. I will locate my basis functions at the C's. That's the idea. And so it looks something like that. This notation is doing a lot of the heavy lifting here. There's a lot of stuff hiding in there, but it's correct. So the idea is that you have some kernel. It has to be a matrix valued kernel for all this to work out, but I've shoved those details into the notation. And the kernel is a continuous function of coefficients, right? And so now you can get the output coefficients as a function of the input coefficients. And so that's just another linear solve to find what that function is. Let me just emphasize here, by using kernels on the input space and the output space, and using kernels to go from the input space to the output space, we get error estimates for free based on smoothness of the input functions, smoothness of the output functions, and then how smooth the D's are with respect to the C's. A priori error estimates, meaning one knows, right? We also, anytime you have a kernel interpolant, you can think of it as the mean value of a Gaussian process. It's the posterior mean of a Gaussian process. So by having this sort of 3 kernel framework, you get 3 GPs, 3 Gaussian processes free, well, for free, for computational cost, right? Training, anytime you want to learn the C's or the D's or the A's, that's just one linear solve, right? And generalization is one dense matrix vector product, and that's it. So putting it all together on one slide, solve one interpolation problem where you fit all the input functions. Solve a second interpolation problem where you fit all the output functions. These are your training data that came from some PDE solver or something, right? And then solve one more interpolation problem that maps the input coefficients to the output coefficients. That's it. Solve 3 interpolation problems. At generalization time, someone gives you a new input function you've never seen before, and you want to find the new output function, fit the new function again, find the C corresponding to that function, and then shove it through the map that we just figured out and get the Ds free. Okay. You might say, well, how will that possibly work as well as neural nets? I'll show you. Right. So let's take a couple of fluid flow problems. This is work in progress. But here we're learning a map from sort of a boundary condition, but it's the initial condition because you're filling space with zeros. But this is lid-driven cavity flow. You have fluid in a box. You move the lid. And in this case, they're moving the lid smoothly. And the other walls of the box don't allow fluid to leak out. See what develops, right? And so here's an interesting plot. These are relative errors versus the number of basis functions. This is DeepONets. So sort of the relative error is reasonably small. This is what people have become accustomed to seeing in operator learning. These are relative L2 errors on functions we've never trained on. So new functions that we're seeing. And so 10 to the minus 2 sort of, that's already reasonably good. If you asked operator learning folks, they would say, oh, that's nice. We can do an order of magnitude lower. There's a subtlety here that I'm going to mention. There's an important issue, a way in which we win, because our interpolants are divergence-free, right? This is just errors. Just by doing this, we have lower errors. If you look at the total training time, because we just have to do some linear solves, we're orders of magnitude cheaper than training a neural net. We also generalize really fast. It's matrix vector products. So all this maps to the GPU just fine. But this is the real winner here, right? Which is if you actually compute the divergence, you're solving an incompressible flow problem. Your velocity field should be divergence-free. If you use standard operator learning, existing techniques, without doing something special, the divergence is like 4 or something, which, in MHD, magnetic monopolarity, right? You don't want that. In this case, our divergence is at machine precision. Oh, I think this is a true statement. We train in double precision, and our neural nets train in single precision, and we're still orders of magnitude faster. Okay, the total number of parameters, we have one parameter for the kernel on the left, one parameter for the kernel on the right, and then one parameter for the kernel in the middle. We learn 3 parameters. Here's a more interesting problem, which is flow past a cylinder. My student made this plot yesterday or the day before. It looks kind of retro and cool, like how fluids would flow past cylinders in the 60s, right? But basically, on this problem, you can really see, right, that there's dynamics. Our method sort of gets 5. It's something on the order of 10 to the minus 6 on generalization. That's a relative L2 error. So we get 6 digits of accuracy. This is what we're accustomed to getting from numerical solvers, but we can get that from operator learning. Current methods barely struggle to reach like 3 digits. We said that's not fair, right? That's not fair. Like our methods are divergence-free. Existing methods are not. You should have made existing methods divergence-free to compare them. We did that. So if you do that, you sort of trade off accuracy and divergence-freeness. You have to tune a penalty term that keeps you divergence-free. I think people who do MHD have done things like this also and have observed similar things there. And so, yep, again, we're analytically divergence-free. If you force your DeepONets to try and stay divergence-free, they'll sort of get down there, but notice the error is still up here, right? So you've traded off divergence-freeness for errors because you're competing loss terms. Okay, so the outro here is the kernel and GP methods have only 3 parameters. They're analytically divergence-free. They achieve state-of-the-art accuracy on real-world fluid flow problems that we've tested so far, sometimes by orders of magnitude, 4 or 5 orders of magnitude, right? And they're interpretable because we understand kernels, we know we have error estimates for them, we know how they work. Okay, the one good slide that I promised, right? The implications for astrophysics. Let's try and wrap it all together, right? So we talked about the KNO, the kernel neural operator in the beginning, which just is the FNO with explicit kernels and quadrature. In astrophysics, you're often working on unbounded domains or really large domains, right? You can pick a quadrature rule tailored to that domain. So for instance, if you know you're doing something in free space, pick the Gauss-Hermite quadrature rule, which is designed for free space, right? Or a truncated Gauss rule that's adaptive And it's probably better than a Gauss-Helming proof. If you don't want magnetic monopoles, which, it's a choice, I guess. But if you don't want magnetic monopoles, you probably want to use the kernel or GP method to get something that's analytically divergence-free, not thrown on as an afterthought. If you want to scale up any of your neural operators or any of your surrogate modeling techniques to millions of degrees of unknowns, you can use the partition of unity formulation that I laid out a few slides ago. And, basically that works. People have been doing this in the kernel method literature for a very, very long time. And it works beautifully. People have been doing it in finite elements for a very long time. It works well. I sort of tried to sort of step out of my comfort zone. Right, so there's these 3+1 formulations of general relativity, if you're doing numerical relativity, right, where you specify an initial condition and then evolve forward in time. In cases like that, if you know what properties the solution must satisfy, if you know relationships, say between the entries of the Ricci tensor or something, you can actually construct a kernel that analytically satisfies those properties and then use that as your operator learning technique. And when I say operator learning, I'm saying replace expensive solver with surrogate model. The emphasis I want to make here is the final approach that I presented, which just 3 interpolants, that gives you uncertainty quantification for free because you get 3 Gaussian processes, one with each interpolant. You also get generative models. We don't think of Gaussian processes that way, but they are. You sample the posterior distribution, you get generative modeling. And so you get generative models for free if you want that. So last slide. So the last slide here, right? So in our kernel method, we're solving 3 linear systems. They're dense linear systems, so they're expensive to solve. In our problems, we tested on small degrees of freedom, like the most we've ever gone to is 10,000 points. But like I said, the machinery exists in the interpolation literature to scale this to millions of points. And people have done that for numerical weather prediction, combustion modeling, right? It's been out there for a long time. And so you could combine that partition of unity stuff that I talked about with the kernel stuff here, and everything scales and is not embarrassingly parallel, but easily parallelizable on the GPU, MPI, whatever. The white whale of fluids is shocks, right? One of the white whales of fluids. And so one of the things we're working towards is kernel methods for shocks, for learning shocks in compressible flow, or even steep gradients. I talked to Stella like last week, Stella Hoffner, and hopefully we'll start collaborating on MHD stuff. That might be fun. And then Hari Sundar, who was here, Professor Hari Sundar was here, is now at Tufts. He and I talked just a few days ago, and we're going to start working on general relativity stuff. And so, yeah, this sort of interpretability accuracy slider, and then my secret title was kernel methods are awesome. And they are, I think. That's the preprints for our work. We're actually updating the KNO paper. We should have a new draft up like in a couple of weeks. But there's something already up on the archive. The ensemble and mixture of expert stuff was accepted at TNLR, so that's that. Okay. Thank you.
It's great. So we can have some questions either in the room or if you ask on Slack, on Zoom, I can read the stuff on Zoom if you can hear me on Zoom.
I'm going to grab the water bottle. Sorry. Could you pass that?
Oh,
thank you.
Yeah. So questions, even kind of basic questions about like some of the machine learning stuff work, will also be there. We'll start with a question in the room. Thanks.
Think to you, yeah.
Yeah, well, yeah, it's supposed to be cool.
Yep.
But like I was thinking, so like I have a problem that can be formulated as a flow, right? But you don't have this string property, this string concentration model. So if I wanted to throw a kernel together, like what would that look like?
You could write a kernel that respects the conservation law analytically over some space-time interval. I'm offering no guarantees on extrapolating beyond that interval because you've engineered the kernel to be nice in that interval. But yeah, you can engineer kernels that respect conservation laws. I should also point out for you, it might be useful. There was a paper in 2021, I think, or 2022. It's called neural conservation laws. So they embedded a conservation law into the forward pass of a neural net so that whenever you evaluate it, it'll always satisfy the conservation law. So that's also an approach you could take. Yeah. Oh, sorry, go ahead.
Yes, so there's a question on Zoom from Jacobo. Selecting physically appropriate gate elements, for instance, divergence-free instead of orthonormal polynomials, for instance, can't comprise function approximation as then modes you need for the finite space to approximate the function. Maybe you come down this, but you.
Yes. Yeah, no, that's an excellent question. So so the question is, if you have these if you pick your basis to satisfy some physical property, do you sacrifice approximation power? The answer is no, right? As long as you take that, if you apply the divergence-free basis to some scalar value problem, all bets are off. But as long as you're applying it to a vector value problem, there are estimates going back, at least with the kernels, there's estimates going back, what, 20 years? There was work from Narkovich and Ward, Wendland. Even I've written a paper on this stuff. Yeah, you can even write fluid solvers using this stuff. So that works. But you have to engineer your kernels carefully, right? If you get the calculus wrong, if you get the initial formulas wrong, then you will compromise accuracy. And in fact, our results also sort of demonstrate that, right? So using our divergence-free kernels, we I mean, come on, it's awesome.
So for you talking about taking the input function stuff and then yourself to think about.
Yes.
What guarantee does it not exist in the input as well?
It's a good question. So it depends on the operator learning problem. That's a problem level question, right? So you're asking, for instance, is there a map in this problem? Let's take this. Is there a mapping between the initial condition and the solution at some final time t? In this problem, we know there is, right? If someone just gave me general data, there is no guarantee. All you can do is maybe learn a map and hope it's good enough, right? In our case, I can answer something a little more sort of mechanical here. If my coefficients are not all the same, or as long as two coefficient vectors are not the same, because I'm learning the mapping between coefficients, this kernel matrix will exist, and this interpolant will exist. Whether it recovers something reasonable depends on the data that you have in the first place. So of course, as always, you're limited by the data that you have. Is that, yeah.
Yeah, so one quick thought would be analytical relation to be expressed as intimacy.
Yes.
It's basically serve as some sort of basis, right? It's a combination of all the bases.
Yes.
So can I extract these bases from the
Yes,
okay.
you can. You have to be cautious though, because you have to ask yourself where the bases live in this diagram, right? So if your goal is to learn the solution from the initial condition, there's actually no specific basis for that in the space-time case, in the most general case of PDEs, right? So if you want to learn that basis, that has to live in this map down here, right? You can specify natural bases on the left and right, but in the middle, you probably have to learn something. In DeepONets, you learn something there. It's called a branch. But again, that doesn't give you a basis. It gives you the coefficients for some basis in the output. There are people working on things like this. This is not quite my area of expertise, but the closest that comes to what you're talking about is something like dynamic mode decomposition, Koopman theory stuff that some folks do, which is essentially solve an eigenvalue problem to recover something like a basis for the space-time domain or for the time domain. Yeah, and that's an interesting problem of its own, not quite what we're doing. Yeah. Yeah. I don't want to give away the secret sauce. No, I'm kidding.
Can you repeat the question?
Yeah, so the question is, how do you extend these physics constraints to more complicated physics constraints? What I can tell you is the following. So there's certain constraints that are natural to bake into kernels. So for instance, if I know the flow is periodic, make a periodic kernel. If I know my fluid flow problem is multi-scale, then make a multi-scale kernel, which is a sum of kernels on multiple scales. But it takes this sort of mindset of engineering the right kernel, which is a different perspective from throw a lot of parameters and learn something, right? And they're all equally valid perspectives depending on the problem you're trying to solve. So for conservation law, you'd have to ask yourself what it means for a kernel. Can a single kernel by itself conserve something, or is it the combination that needs to respect the conservation law, right? That, spoiler, it's the combination. But yes, yeah.
Thinking of the beginning examples of doing operator learning, the majority of the examples are, we have some forcing that's an input function and model and an output function. And for the PE that's at terminal time t. You mentioned also including time and additional argument or the
Yes.
mentioned.
Yes.
And there is, it sounds like a much harder problem and it kind of being tackled by pins. Have you done much work in this? What type of, how difficult is it to parameterize it? It seems like you should talk about spatially, you expect things to be in a certain way, but you figured out you can't help things with working time.
Yeah. So the question for Zoom folks is, how does this extend to space-time settings? So I just want to make a quick note on something you said. Pins don't quite solve that problem. Pins are trying to solve the PDE itself, right? Or learn some terms in the PDE. You could leverage pins to do some of what you just said, but let's walk it back. Let's take the kernel neural operator. Just way back. Yeesh. Okay, so now omega is a space-time domain, right? You want a kernel that's a function of space and time. You can try and do things like the GR people would do, which is throw a Minkowski metric into the kernel, which is a space-time metric. And then you have a kernel that's conditioned on space-time. You need more data because you're learning space-time, but that's actually well understood and people have been doing it outside of operator learning for a very long time. You could also choose just like a product kernel, a kernel that's a product of space and one of time. And I'm pointing at this and saying that because that also carries over to the interpolation setting. You interpolate with product kernels or kernels with any metric, as long as it's a valid metric. So I want to, sort of segue from your question a little further. You can also do things on manifolds, right? These kernel interpolation matrices are non-singular on manifolds. And so you can do problems that are not just in volumetric domains, but on surfaces as well. Yeah. So it just does work, but you just need a lot more data. Yeah.
Yes, maybe we'll leave it there. So it's supposed to end of the hour. Let's thank Varun one more time. Yeah, thanks everyone for coming.